Hello everyone, welcome to the third WeSST seminar. I'm happy to introduce our speakers today. We've got Lars Pastewka
from studying the chemistry of life to developing the advanced.
So we've got Lars Pastewka from the University of Freiburg and Guillermo Morales from SKF. So Lars is going to talk a bit about the emergence of surface roughness from deformation and wear processes, while Guillermo will talk about tribology modelling for lubricated contacts for electrification. I'd just quickly like to thank our sponsors, the Royal Society of Chemistry, Swiss Tribology, the Institute of Physics and the Institution of Mechanical Engineers. And now I'll just hand over to Lars, who can get slides up and ready to go. Okay, your screen seems to be going through, Lars.
Sorry, I'll have to unmute my
That's okay.
microphone. Okay, can you see this?
Yeah, I think it's coming through. Yeah, there we go.
Okay, perfect. So then I'll start, James. Is that right?
Yeah.
Okay. Yeah. So let me first of all start by thanking James and Chiara for giving me the opportunity to speak here. I mean, this is these are unusual times, and they call for unusual formats of discussing science. And I think Chiara and James have found something that's very nice, and so it's a pleasure. It's a pleasure to be here and speak about some of our recent results. So my group does mainly computer simulations, or exclusively computer simulations on different scales, and I will talk today a little bit about a couple of molecular dynamics calculations that we have done over recent years, trying to understand why surfaces are rough. I mean, everybody working in aware of the fact that engineering surfaces, almost all surfaces, have surface roughness. And a question that has bothered me is why that is the case, and can we explain this? And I'll show something that is mainly focused around plasticity. And towards the end, I'll highlight recent work by Ramin Aghababay and Jean-François Molinari, who also worked on this topic using fracture models. And I'll show some of their calculations. In a normal conference, I would now wave at them and tell them to yell at me if I say something that's wrong about their work. And here you have to do that through the chat, I guess. Okay, so let me start with surface roughness. Well, this is, of course, a picture that many of you working in tribology have seen. So the typical picture of a sliding system is you have two rough surfaces.
Sorry, Lars.
Contact each other.
Sorry, Lars. Can I just stop you a sec? The screen is slightly the wrong shape. So hopefully everyone can see all of the slide now. Just give it well, about 30 seconds, Lars, just to make sure everyone can see everything. There was a bit of the slide cut off.
Okay. I mean, that is probably not a big issue. Should I continue?
Give me 2 minutes. A little less than 2 minutes. Okay, yeah, that looks better.
Okay, yeah. So let me continue. So the surface roughness and friction. So picture that's typically drawn is looks like this. Two surfaces touching each other, two rough surfaces, and of course the area of intimate atomic contact is limited to the peaks of the asperities of the two mountain ranges that touch here. Then we have a force pushing them together, and of course a sliding velocity. So this all happens under external load. And what happens, and in particular in metallic sliding systems, is that of course the surface deforms. And what you see down here is a picture that I've taken from David Rigney's work, who has looked at mechanically mixed layers for much of his career. And the picture that's typically drawn is that of a plastically deformed zone. And what these lines indicate is sort of the shape of the plastic deformation. And it seems to indicate that plastic deformation is a laminar process. There's, of course, if you look at this carefully, there's something that's called a very highly deformed region where something else may be happening. But let's for a second pause and think about what it would mean if the plastic deformation was really a laminar process. So we have these rough surfaces, we have these asperities touching, and of course, because of plastic deformation, what would happen is these asperities deform, and they would flow to fill in this void region that you see here. So it's probably to be expected in a sort of a naive way that the two surfaces would at some point become perfectly flat. And of course, they don't do that. I'll show you in a second an experimental example where this is shown. And the reason they don't do this, and what I would like to focus today, is that plastic deformation, subsurface plastic deformation, is not a laminar process. So this idea of plastic flow being laminar, that's, for example, encoded in continuum models, J2 plasticity models of deformation, is something that doesn't work at small scales. So I promised a little bit of an experimental result.
Sorry, Lars, can I just stop you again? It's still not showing correctly on everyone's screens at the moment. Let me just have a go at.
Is it showing okay on your screen?
It shows okay on the meeting. It's the stream it's cropping you can only just see the top right of the slide. I mean, we might have to make do with it for now because I can't see an obvious way of improving it, because it looks fine. It looks fine on my screen, and in the meeting it's just the stream. So I suggest we carry on, and I'll try and sort it out in the meantime. Sorry.
I mean, if it's Zoom, I could try to. This is a high resolution screen. I could try to switch to a lower resolution screen. I'm not sure.
I'm not sure. I'm not sure. I don't think it's your end. I think it's my end. So I suggest, just carry on for now, and we'll try and sort something out in the meantime.
Okay, sounds good. So what can you see on this screen? Can you see the plot on the top left?
Yeah, I can see that part. It's the bottom right that's missing.
Oh, the bottom right. Okay,
yeah.
Okay. So what this plot shows, I mean, this is experimental work, sapphire sliding on aluminum by Pancho Stoyanov, then working with Martin Dienwiebel and Richard Kromick, and this shows the friction coefficient. This is the y-axis and the red curve here. And it shows the surface roughness measured in situ during this experiment. And what you see in this case is some sort of running in, a bit untypical since the friction coefficient actually goes up, but at the same time the surface roughness goes up. So there's not many experimental results of this nature in the literature, but some indicate that surfaces don't just flatten during sliding, but they can also roughen, and there seems to be some steady state surface roughness that develops during frictional loading and during wear. So before starting about my take at why something like this happens, let me briefly discuss surface roughness. So this is a slide that I've shown a couple of times, and since this is now on YouTube, this is probably the last time that I should show it. And when showing this, I like to ask the question that these are three realizations of a surface topography. Does anybody want to guess what material this is? And of course, that's a question that cannot be answered. These look very similar, but they also don't have a scale bar. So if I show you the scale of these measurements, then it immediately becomes clear that this is something completely different. So the left one you see is kilometers. This one is nanometers, and this is AU, arbitrary units. And so the left plot that you see here is actually a section of the Alp mountain range. This is a AFM scan of an ultra nanocrystalline diamond surface from Tevis Jacobs group in Pittsburgh, and this is a computer generated surface that I generated in the computer. So the goal of this exercise is to illustrate that, well, if I take something that is really large scale, this Alp mountain range, and I rescale the positions by a certain factor, and I rescale the heights by an appropriate factor, then I get something that is virtually or statistically indistinguishable for something like, for example, this ultra nanocrystalline diamond surface. And that is a property that is called self-affine scaling, in this case, statistical self-affine scaling. And what I've just illustrated to you in a sort of visual manner can be made a bit more formal. So we can ask the question, if we look at a surface, what is the variation in surface heights or in the difference of the height between 2 points? So imagine I'm sitting on the point to the left of this black arrow here, and I'm asking the question, what is the difference in height to a point that is at the end of this arrow? And I'm doing this now for all points, let's say a distance L away. Then what I get is, of course, I get something that looks like a rough profile. So I get, of course, different height distances depending on where the arrow sits. But I can ask the question, what is the amplitude of that height variation at a distance h, at a distance L? And it turns out that for many, many surfaces, or in particular for surfaces that have these self-affine scaling properties, this height variation delta h scales with the distance to some power of capital H, which is called the Hurst exponent, and h is between 0 and 1. This seems to indicate that these distances grow unbounded, but let me illustrate that this is still a flat surface. So if we ask the question, what is the mean height over this distance L? So if I do dh over L, then I get scaling that looks like this, L to the power of minus 1 minus h, and this is a positive number, this 1 minus h, so this actually goes to 0 as I look over larger and larger distances. So these are nominally flat surfaces. So this is one way of sort of looking at this self-affine scaling. There's different ways of detecting this. This would correspond to computing something that's called the autocorrelation function, the height difference autocorrelation function on the surface. What we can also look at, and what's more common, is looking at the power spectral density. So this plot shows on the left-hand side the power spectral density, in this case as a function of wave number that also corresponds to the length scale we are looking at. And similar to the height differences that scaled with L to the power of h, here we find power law scaling with a wave vector to the power of 1 minus 2h, and this is an indicator for self-affinity. So this data set here is remarkable. It's the largest continuous data set that I know of out of the group of Emily Brodsky on geological faults. And you see measurements ranging from 100 kilometers in length scale down to 0.1 millimeter. And you see that this power law scaling seems to extend over these many decades in length, and the exponent that they find is of the order of 0.8. The right plot is taken from one of Beauperson's papers on a steel surface, and you see that even if you look at smaller scales, in this case steel, you often find the self-affine scaling properties here down to measurements of the STM. Hurst exponent, so the value of these scaling exponents are often between 0.7 and 0.8. So why is this the case? What are the origins of surface roughness? I mean, there's different things that have been done in the past. There's a lot of work in the literature actually on surface growth. So if you think about CVD or PVD growth, there's growth models that physics communities have looked at. They do lead to self-affine surfaces, often with a Hurst exponent around 0.5. The two most famous models are probably the Edward Wilkinson and Kadar-Parisi-Cheng model. But of course, the surfaces that we look at are not mostly not grown. There's erosion models that also predict self-affine scaling. This is one example of Beauperson's work that predict a Hurst exponent close to 0.1. But I would like to argue that most of the interfaces that we look at are actually interfaces that have experienced deformation. So they have been machined, they have been polished, and then we use them in a tribological context, so they have been worn down. So they experience plastic deformation and fracture. So why would deformation lead to surface roughness? So the very traditional view of how roughness emerges, in this case in a polycrystalline metal, is imagine you have a microstructure such as the one shown on the top right here, where the color indicates essentially grain orientation. In this case, it's a Schmidt vector, which tells us how the grains deform. And let's assume that the grain orientation is different. So some of these grains deform easily to some sort of applied load, and others are more resistant. Then of course this will lead at a surface to the evolution of a topography. And this is what's shown in this red image here on the right image here. I will show you later that we think that this doesn't give rise to self-affine surface structure, while it gives rise to, of course, surface roughness. On the other hand, there's some very interesting work now on actually single crystalline materials. So this, of course, the material microstructure represents material heterogeneity of the material. And what you see down here is now the autocorrelation function of a surface scan, an experimental work out of Michael Zeiser's group who's now in Erlangen, from the compression of single crystalline potassium chloride and lithium fluoride samples. And you see that on these single crystalline samples without any heterogeneity, you also find surface roughness, and you indeed find surface roughness after deformation that is self-affine. In this case, scaling exponent or Hurst exponent close to 0.8. So we took these ideas. So Michael Zeiser has these experiments and has done also a bit on modeling these systems, but nobody has looked at this before with molecular methods. So we said, why don't we just set up a very simple molecular dynamics calculation? So this is a homogeneous piece of material. In this case, this is a copper zirconium glass. It's actually a slab. It has two free surfaces. So what you see in red on top here is one of the free surfaces, and the other one is at the bottom. And we now expose it to a very simple type of deformation. So we do simply compress it along these axes that are indicated by these red arrows. So again, in this laminar idea of deformation, what should happen is that simply the slab should become thinner, and this surface should move up. But let me run this calculation for you. What you see is that even though this material is perfectly homogeneous, what we find at the surface after this calculation is that the surface has become rough. So there seems to be something intrinsic to the deformation process that leads to surface roughness. Now the glass is, of course, I said it's homogeneous, but really at atomic scales there is the glassy heterogeneity. So we did these calculations for 3 different types of systems. For single crystalline gold, these are 111 surfaces, for a high entropy alloy, and for this copper zirconium glass. And these systems represent different limits of being perfectly ordered in case of the single crystalline gold, of course, where each atom sits next to each other, having stoichiometric disorder. This high entropy alloy, so it's an FCC lattice, but then with random elements, nickel, cobalt, iron, and titanium, with the composition shown down here, and of course this glassy material that has disorder at the atomic scale. And all of these develop surface roughness. So on the crystalline system, you nicely see these little triangular structures that of course represent the lattice plane of the crystal. And what you see here is a 111 surface, and these are actually the slip planes of dislocations that exit the surface. I'll come back to that in a second. This is the high entropy alloy that looks similar, and the glass is smooth. So while running these calculations, we can of course monitor stress and also the surface roughness. So these plots show on the x-axis the applied strain in the system. The top one is a classical stress strain curve. So let me just point out that there is, of course, an elastic regime, and then we have these huge stress overshoots for the crystalline systems because they are defect-free. So this is, of course, sort of an artificial situation, but it's exactly what we wanted to test. And then these materials flow at almost constant stress as we continue to compress. So this is the root mean square surface height. So it's the amplitude of the height fluctuations. If this is a line scan of our height, it would tell us by how much, of course, the amplitude varies. And I'll show that to you in a second as a function of scale. So this is now the height measured over the full size of the samples that you see here that were initially 100 nanometers by 100 nanometers. And you see that the roughness increases as we strain it. But yield is the point where it emerges first. So before the material has yielded in the elastic regime, there's no surface roughness. Now we can look in a little more detail. We can again come back to this question of self-affinity. And what we've done is we haven't looked at the power spectrum. We have used a little more direct measure of self-affinity that goes back to what Mandelbrot has done a couple of decades ago. So we look at again at the amplitude of height fluctuation. So this HRMS now as a function of scale or length. So if the scale is equal to 1, we are measuring HRMS over the full size of the system, for equal to only over half of this, and so on. So essentially, we are measuring HRMS in these little squares and vary the size of these little squares of this grid that I've plotted on the surface in the left plot here. And what we see is shown here: y-axis HRMS, x-axis magnification. Before yield, these are the blue curves down here. There's after yield, it jumps to a power law behavior of HRMS as a function of magnification, which indicates self-affine scaling of the surface topography. So we can actually do a little more in detailed analysis. This HRMS is, of course, simply the width of some underlying height distribution function. We can now look at the full height distribution function. This is what's shown on the right, and we can rescale the heights that we find. So this is the h here by the magnification and the Hurst exponent. So we can rescale all heights such they are normalized, and we see that during the whole deformation process we can collapse the full height information onto a single master curve, and from this, of course, inversely we can predict how the height distribution evolves as a function of scale throughout these calculations. There's something else that we can do in these calculations. We cannot just look at the surface, but we can also ask the question, what happens subsurface? So what we've done is exactly the same analysis as on the surface in the subsurface region. So we are now asking the question, by how much does an atom move in the direction normal to the surface? At the surface, if we ask this question at the surface, this gives us a surface topography. In the surface, it gives us a measure for the deformation profile. So we again do this in these little boxes, and we change the size of these boxes. So here the x-axis is the size of the box. And of course, all the atoms move in slightly different directions. So we can again ask the question, what is the width of the distribution function that governs the movement of the atoms? And we see something very similar to the surface. We can collapse that onto a single universal curve. So what we see at the surface here is nothing else than a signature of the non-affine or non-laminar deformation profile of the subsurface deformation in these systems. Of course, we can extract the Hurst exponent from this analysis. So this is again on what you see on the top right is stress as a function of strain. This is a stress-strain curve, and down here you see the Hurst exponent, now extracted from our surface analysis and our bulk analysis. They are very close for the high entropy alloy and the gold, and the high entropy alloy gives us something that is on the order of 0.7, what's often seen experimentally. I'll come back to the gold in a second. The gold gives us almost 0.5, and I would like to illustrate to you why that is as a very simple explanation of what we are seeing here. And the copper zirconium is something that we are still working on that is actually highly temperature dependent. I don't have the data on these slides. Okay, just comparing to Michael Zeiser's work that I've shown before. So this was the scaling on potassium chloride and lithium fluoride. This is close to what we find actually for these multi-component alloys in our systems. Okay, so what's going on here? Why do we get self-affine scaling? And it's actually very simple to explain for a crystal in which the dislocations move uncorrelated. So if we have a dislocation as the carrier of plastic deformation in a crystalline material, then when that hits the surface, it will leave behind a step on that surface, a step of that with a height that's correlated to the Burgers vector of that dislocation. So let's make a rough surface on this little square that you see on the right. So I'm just throwing onto the surface a random step. So when I come from here, when you see my pointer, I'm moving towards the step, then I would move up by a little bit by Burgers vector when I move over the step. And now we do this randomly on the surface. And when we do this randomly, we get a surface that looks like this. Here, the directions are now simply chosen from the slip directions on an FCC 111 surface. But if I look at the power spectrum that I get, I actually get something that is H.5. And this makes perfect sense, because what I'm doing, if I'm sort of scanning across this surface, I'm just moving up and down in a random fashion. So this is a random walk, essentially. And random walks are well known to have these scaling properties. We can also look at this from terms of the Fourier transform, looking at the Fourier transform of a step function. This is 1 over q, and this leads to also this H.5 result. So it's sort of trivial if you think about this for metals, but for in which dislocations move uncorrelated, but it's sort of you can reconciliate it with sort of a Laminar idea of material deformation, and then when the dislocations become correlated, this gives rise to different values of the Hurst exponent. Coming back to this question of what happens for laminar models, so this is a continuum calculation that we have carried out, in which we have said, let's assume we have actually a heterogeneous material in which the yield strength in sort of subsurface volumes of the material here indicated by colors differs randomly. And then we compress it. We get a random surface that's shown on the top right, but our scaling plot does not show self-affinity. So this is sort of this picture of having different grains and different orientations that deform and give rise to surface roughness. Okay, so I hope I could convince you that this, of course, this idea of laminar flow is doesn't make sense at small scales, and that there is a mechanism that actually leads to the creation of new surface roughness. Let me, for the last couple of minutes that I have here, talk about brittle materials. So this is, of course, a mechanism that depends on plasticity. What happens if the material is brittle, if we have cracks in the material? So the first point that I want to make is that plasticity is a question of scale. So this is a picture taken from an old paper, 1949, in which Taylor did the indentation experiment and noticed that if there were very small indents, this was a glass, I think a soda lime glass, the glass behaved perfectly plastic, and for deeper indent it would fracture. And if you look into fracture mechanics, of course, the stress near a crack tip becomes very large, and there is always, or in most materials, there is a region that's often called the process zone, in which something happens that is not elastic deformation, but that is plastic deformation. So at small scales, even in cracks of brittle materials, you will have plastic deformation. One system that we're currently looking at is amorphous carbon, which has a process zone on the order of 10 nanometers. For all metals and most ductile materials, the process zone is too large to be able to simulate it in molecular dynamics calculations. So maybe amorphous carbon is one of the only systems, or the few systems, that has a process zone where some plasticity happens. Here the color indicates the change of coordination number of the atoms near the crack tip, where we can say something about fracture. This is, of course, brittle crystals aside, silicon and diamond are perfectly brittle. So you have to do something, and this leads me to some beautiful calculations out of the group of Ramin Akababai, who is now at Aarhus, and Jean-François Molinari at EPFL, who used a specialized model. So they call it molecular dynamics. I would probably call it discrete element model. Sorry, Jean-François, if I'm deviating from your nomenclature. But what they did, and what is very clever, is they designed their model in a way that the process zone is small, so that they can do simulation sizes much larger than the process zone size. And this is one of their calculations from Nature Communications that was published last year, in which they set up a rough surface. They slide on top of each other, and they see the formation of these wear particles. But what they did in this paper is they actually analyzed the surface roughness after their sliding calculation has finished. So they slid for a very long distance. And the right-hand side here again shows the power spectral density of their surfaces. So power spectrum is a function of Q, and they also find self-affine scaling with H on between 0.5 and 1 on the order of 0.7. So this means at small scales we have plasticity. There's intrinsic plastic processes that I described to you. At larger scales we have fracture mechanics, which is sort of the gist of this model. And this seems also to be corroborated by experiments. So these are two examples from the literature. The left hand is a crack on silica glass from Laurent Ponson, Daniel Bonamier, and Elisabeth Bouchot that shows that there seems to be a scale below and above which the crack properties change. So this is again the delta H, so the autocorrelation function is a function of distance. And you see that these scaling properties change at some point, and this length scale probably corresponds to the size of the process zone. The right one is sliding rocks, again from Emily Brodsky's group, that shows something very similar. A length scale below which, in this case, the surface becomes isotropic, above it, which is it's anisotropic, but there's also a change in scaling exponent for some of the directions. So there seems to be a change in mechanism at something on the order of the process zone size. So what I've talked mainly about today would be the mechanism for the evolution of small-scale roughness. Jean-François and Ramin have done beautiful work on what happens at larger scales. So this is what has happened recently in the simulation community. What's left to be done, of course, is think about how this can be translated into experiments and what practical implication this has. But I think that thinking about how the surfaces that we work with or the morphology actually develops and evolves, and that morphology, of course, in the end controls friction and wear and other things, is important and is something that we should continue to think about. So with that, I'm at the end. Let me thank Adam Hinkel and Wolfram Nöring, who did the major part of the calculations that I've shown to you today. Let me thank the ERC for funding and the Gauss Center for supercomputing for granting us with very large amounts of computer time that made these calculations possible in the first place. And of course, again, thanks to Chiara and James for putting this this nice online seminar together.
Thank you very much, Lars.
Thank you very much. I have a couple of questions for you. So the first one is, clearly it seems that the dislocation behavior and the emergence of roughness are closely related to one another. And I wonder if you can say maybe a bit more about what about the dislocation behavior, the sort of energy needed for dislocation formation, the concentration of dislocations.
So yeah, so our calculations were initially dislocation free. So we have homogeneous nucleation or nucleation from surfaces. So it's something that we are still looking at. But let me point out that it looks like this is not tied to dislocations. I mean, this was part of the exercise of using this glass structure, was to have a material that has a completely different mechanism of accommodating deformation. That has nothing to do with dislocation. It's shear transformation zones. It's local regions that flip under an external stress. And the dislocation, sort of, I put a little bit of focus on here because we understand, let me say, more about why this leads to self-affine surface structure. For the classes, we are still actively investigating this, and Wolfram is currently preparing a manuscript on what's happening there. And I do believe that if you look at plasticity at larger scales, so think about shear bands and other mechanisms of accommodating strain that occur at larger strains, that maybe something like this would also emerge. And again, we are looking at this actively, trying to understand why this leads to this self-affine structure of the surface roughness.
Okay, thank you. Okay. Yes, so there is a question from Ramin Agababe. I hope I'm pronouncing your name right. In a slide, you showed Hurst exponent. And have you looked at the evolution of the shear stresses on the surface?
First of all, hi Ramin, and so you were talking about the slide that shows the Hurst exponent. Is this one? Shear. I mean, the surface is the traction is traction free because we have a free surface. So we didn't really look in detail on the intrinsic stresses subsurface. This is what we find for the Hurst exponent in our systems. So it differs from these three systems. We don't really know why it differs in the way that that you see here. but what we can say is that it seems to be relatively invariant with strain. And indeed, if we look at the structure that forms, if you take a visual image of the surface structure, it seems to be sort of imprinted on the system at the point where the material yields, and then it evolves further. But the main structure seems to remain the same. So we're currently trying to quantify this by looking at cost correlations between the topography maps obtained at different values of the strain.
Okay, thank you very much. I think this is all the questions we have time for now. If your question didn't get answered, Lars will answer it offline after the end of both talks. And please, if you have more questions for him, keep on asking them now in the comments. And now over to James.
Thanks. So Guillermo, if you could share your screen now, please, and Lars, stop sharing.
Yeah, I've stopped sharing.
Thank you very much.
Okay.
Okay, so our next speaker is Guillermo Morales from SKF. He's a principal scientist at SKF. He's also a visiting professor at both Imperial College London and INSA Lyon. His talk today is on tribology modelling of lubricated contacts for electrification. Take it away, Guillermo.
Thank you very much, James, and thank you for the invitation, Chiara and James, to participate in this webinar. Let us see if all the technology works. I will talk to you about tribology modeling of lubricated contacts for electrification. This is basically a summary of the work we are doing in SKF to tackle the new challenges brought to us, mainly by electrical mobility, as you will see. Presentation is divided in 4 chapters, so we will discuss a little bit the challenges in lubricated contacts, modeling of lubrication, modeling of failure modes, and then at the end, modeling of life of these contacts. So let us take the first one, challenges in lubricated contacts for electrification. When I was designing the talk, I had this dilemma whether to focus the talk on describing the actual process of damaging a contact through electricity and modeling the electrical circuit, or focusing more on the new challenges brought to us in the operating conditions for these contacts, like different temperatures, different speeds, and different chemicals. And then, since there is quite a lot of literature on this topic, I decided to go for the other one, which is more the challenging application conditions that the contacts have. So the first thing I would like to do is to discuss briefly with you what are those tribological challenges brought to us by, for instance, full electrical vehicles. So if we start analyzing these vehicles, we soon realize that the electrical motors are sealed for life, that also the bearings in the electrical motors are subjected to very high speeds, very high accelerations, and very high temperatures. And that, of course, brings to the contact challenges about what to do to have long grease life, long surface life under variable conditions, and especially issues like surface distress, seizure, or adhesive wear that these contacts will see in very high speeds. There is another important extra element, that is that these electrical motors are running at very high speeds in order to be efficient. And that brings also the possibility to introduce higher torque and higher loads in the contacts. So again, what to do about the life of the contacts under those conditions. Then there is the fact that we are introducing quite a lot of new materials in the system, like copper wires, coolants, and advanced polymers. And then we need to deal with the compatibility with electrical currents and magnetic fields. that brings important challenges in the contacts because there are unforeseen consequences in lubrication. There is also the possibility of increasing the solid contamination due to corrosion and the other elements that we have there. Now, since we are running the motors at high speeds, there is also the need to lower the speeds in the system by having high transmission ratios in some gears. So some gears will actually be running at lower speeds and high torque conditions. That brings very tough conditions for the contact life. Again, the life of those contacts under poor lubrication conditions and surface distress. There is also the possibility to have chances of electrical damage in the contacts, fluting, electrical erosion, etc. And then we need to understand how this damage propagates in the surface. Then we need to run these contacts with less allowed noise. We need to improve the lubrication conditions in the contact. But with the contradiction that we are more and more using lower viscosity lubricants. So surface distress is coming up again as an important potential failure mode. Now, when we have hybrid electrical vehicles, we add an extra element, which is the combustion engine, but the conditions will not be too different from these ones. So I would like to move on to the summary of the new challenges. We are talking about poor lubrication conditions in the contacts, high speeds and accelerations, surface life, high temperatures, surface distress, long life, and lower viscosity. This is the new reality when it comes to electrical vehicles. Now, even before electrification, we had already very important challenges in those contacts. Let us just have a look of bearings and gears. If we talk about bearings, you can immediately see that the normal operating conditions in bearings in automotive applications take loads which go from 3 to 4 gigapascals pressures. This is really high pressure. The number of load cycles that these surfaces have to endure can be up to 1 to the 10 to the power 11. The field thicknesses are very low, about 100 nanometers. Sliding conditions go from 0 to 2% in the loaded zone, and that gives us some shear rates, which are about 1 multiplied by 10 to the power 7, reciprocal of seconds. This is very high shear rates. Gears work under slightly lower loads, 1 to 2 gigapascals. The number of cycles that we expect to endure is also a bit lower, 1 multiplied by 10 to the power 8. The field thickness is a bit thicker, but we need to remember that the surfaces of gears are, the roughness is higher, so in reality, the lambda ratios is about the same as the bearings. The sliding conditions go from 0 to 30%, and the shear rates is a bit lower than bearings. All these with the mega trends of increased efficiency, longer reliability and life, extended maintenance intervals, compactness, reduced noise, and reduced lubrication, together with the fact that at least in bearings, the field thickness has been reduced in time. All these bring us to a situation where most of the failures that we see in these machine elements are surface-initiated failures. So tribology was already important. Now, let us see how we really understand the lubrication in these machine elements, because eventually, if we understand the lubrication, we can understand many of the potential failure modes. We need to understand lubrication not only from the point of view of calculating field thickness and pressure inside the contact, but also what is happening outside the contacts, because what is happening outside the contact will actually determine in many occasions what actually happens in the contact. Now, if we are talking about simulating millions of load cycles, we cannot do this in the old-fashioned way of using numerical techniques, because it takes too long for one calculation. We need to have a more pragmatic approach based on semi-analytical solutions. And this is what we are proposing since many years back. Models that can actually consider the microgeometry of the contact, that also can model the non-Newtonian behavior of the lubricants, time-dependent solutions, mixed lubrication, and thermal effects, and actually modeling the whole topography in a contact. Now, to do that, we have to rely, as I said before, in semi-analytical solutions based on Fourier fast transform. And I would like just to give you a brief idea of the concept. The actual model is a bit more complicated than this, but this is just to show the basic idea. If you have two surfaces which are rough and are lubricated, they will produce a pressure distribution that has these pressure ripples. Now, we do not want to model the whole geometry of the contact because that is very time consuming. We want to focus on modeling the ripples only, the pressure ripples and the field thickness ripples. For that, we focus our attention in the central zone of the contact. Now here, we have very high viscosities. And if we have very high viscosities, the Poisson flow term in the Reynolds equation tends to be small. So we can simplify this equation by just having a wave equation, a transport equation, which actually is linear. And if we know the solution for a sinusoidal, we can apply the powerful Fourier techniques to actually solve any topography that we want. Now, this is a very basic idea. The reality is more complex than this because if you want to deal with non-Newtonian fluid, immediately you realize that you cannot totally remove the Poisson flow. Parts will have to remain in order to model the non-Newtonian behavior. So we need to calculate the equivalent viscosities in the two directions, but also more important, the overall solution for the ripples is made of two important parts. One is what we call the moving steady state of the particular integral, and this is basically describing the deformation of the roughness when it goes into the contact and the generation of these pressure ripples. There is another very important element that at the beginning we ignored, but then we realized that it's important, and that is the disturbance of the flow introduced by the roughness every time a ripple gets into the contact. It will produce some flow variation that will travel through the contact with the mean speed of the lubricant. Adding those two together, we get the full solution of the problem. A lot of the work on this is due to Professor Hook from the University of Birmingham, who has been really working a lot trying to develop these complex models. Now, this is just an example of what the model can do. For instance, if you have an indentation on the surface, you can see that the indentation produces pressure ripples. You can also see the profile of the pressures and the stresses that that produces. This is zero sliding non-Newtonian fluid. The same problem, but now with a surface, indented surface that is moving 30% faster than the smooth surface with a non-Newtonian fluid, you see immediately how the two waves separate because they travel at different speed. So the indentation already has left the contact while the ripple is still inside the contact. And that has important consequences in fatigue as well. Now, we were talking about modeling what happens outside the contact. This is basically the product of what we call kinematic starvation. When we are running machine elements at very high speeds, there is a chance that we induce what we call kinematic starvation. And a good example is a rolling bearing. We define this quality of lubrication parameter, kappa, which is similar to a power of lambda, if you want to put it in more simple terms. And here you have the speed, basically the multiplication of the RPMs by the mean diameter of the bearing in millimeters. And that gives you a measure of the speed. So we know that when we increase the speed, the field thickness will increase until a certain point, but then starvation will take control, and it will actually reduce the field thickness if you keep increasing the speed. And how much and where this will happen depends very much on the lubricant supply that you have in your machine element. If you have a grease that is lubricating this bearing, which is not bleeding fast enough, you will not have enough time to replenish the contacts, and eventually you will run out of lubricant, starving the contacts. The same will happen with an oil supply that is not targeting enough the needs of the bearing. You will see the same phenomenon. Now, there are many ways or many models actually to capture this in a model. But eventually we have concluded that at the end of the day, you need some experimentation because it's extremely difficult to model in advance what are the conditions of the lubricant just in front of the contact. If you manage to do that, then you can model everything, and we can do that in the laboratory, but not in a real machine element. And this is example of what is possible to do in the laboratory in a tribometer consistent of a disc and a ball. You can pretty much model the conditions when you increase the speed. You can model all starvation conditions if you are clever enough in a very controlled way. Now, once we understand and can model lubrication in machine elements, it's time to move towards different failure modes related to the surface. One failure mode that we saw many times in our first slides is what we call surface distress. It's also called micropitting, especially in the USA. We also call it gray staining, microspalling, surface fatigue, etc. It has many, many names, but it's basically surface fatigue at asperity level. And there is obviously a very good, very well-known definition of this failure mode for rolling bearings in this ISO standard. There are also ISO standards for gears describing micropitting. It looks like this when you have a surface. You see these shiny bands here. If you look closer, you see some pits. If you go into the microscope, then you see some clear microspalls. And when you make a cut in the transverse direction, you see that these are really shallow cracks. And this is typically what we call surface distress. It's important to say that although this is basically due to poor lubrication conditions and fatigue at asperity level, there is always a competition between fatigue and wear, mild wear, the kind of wear that modifies the topography only. And if you have too much wear, you may not see surface distress. If you don't have any wear, you may see very quickly surface distress because you don't have enough flattening of the topography. Now, something important to say is that this failure mode depends pretty much on the lubricant that you have in your system. And this is just an experiment that has been published in this paper with my colleagues here, where we have used this micropitting tester that has 3 rings and 1 roller in the middle. So we try to induce the micropitting or the surface distress in the roller. So if you run an experiment exactly with the same operating conditions, the same roughness, and even the same oil, but just changing the additive composition, the description is here, then you can expect very different behavior for the same conditions. And that is precisely because the additives will modify locally the friction coefficient and the wear coefficient. And that has consequences in the stresses that we have in the surface. So another way to study micropitting experimentally is actually by introducing indentations on the raceways, because immediately you will generate micropitting around this rice material, and especially in this area, which is normally the exit of the overrolling. So if you have a ball that is overrolling in this direction, this will be the exit point, and we call it the trailing edge of the dent. And normally here you generate more surface stress, as can be modeled as well. It will also, the model, give you more surface stress here. And this is due to the fact that here we have slightly higher hydrodynamic pressures. But if you really want to model this phenomenon, you need to take into account many, many things. You need to take into account the actual topography that you are testing. You need to take into account also the build-up of tribal layer from the additives. And for that, we use the work of Sang and Professor Spikes in Imperial College, who have established that the tribal layer reaction depends on the shear stress and depends on the temperature. It's important to say that because in the past we used to believe that it depended on the pressure, but he has shown that it depends on the shear stress. So we need to be able to calculate locally the shear stress. And then you will generate a patchy tribal layer, as indicated in this very rough diagram, where we see areas which are separated by the lubricant, and then we see areas which are more kind of dry contact. And therefore, we have locally different friction coefficients and different wear coefficients, because it can be the case that you have a dry contact between tribal layer and tribal layer, or tribal layer steel, or steel. So you need to be able to measure these friction coefficients and wear coefficients in the experiments in the lab. But once you have that, then we can use this model. So you basically measure the tribal layer, you measure the topographies. We introduce these topographies into the mixed lubrication model, the fast mixed lubrication model, together with the lubricant rheology, the operating conditions, the material. We are able to calculate the stresses and eventually the stress history of the roughness going through the contact. With that, we go to a fatigue criterion to assess the damage locally and eventually to accumulate this damage over time. If we have reached the number of load cycles, we report the results. If not, we increase the time. We apply a local wear model. We calculate the local temperatures, and eventually we calculate the local increase of tribal layer. And then we repeat this process many times until we reach the simulation time. And interesting, at the end of the day, we can basically simulate things like what we see in the experiments. Again, our tester here, this is a topography we started with. This is just a very short snapshot of in time of the shear stresses at the surface calculated by the model. And then you can see how the tribal layer is being grown in the rings and on the roller. And it's much faster on the roller because it sees many more cycles. But the important thing is not to stop here, but actually to try to make the link with performance. Because at the end of the day, this is what we are after. And for instance, it's interesting to simulate the same oil with a typical additive, CDDP, but different temperatures. And then you have here the experiments. And we know that in higher temperatures, this additive is more reactive. So you will generate thicker tribal layers, which will prevent wear and will induce more easily surface fatigue. And this is what you see in the experiment. Now, the material so far, the steel has been considered homogeneous. We have seen in the previous presentation that is far from homogeneous. And we are trying to get closer to simulating a little bit more different aspects in bearing steel, but also gear steel. For instance, is made of different phases oriented, or different crystals oriented in different directions, having different properties, and it has inclusions, it has carbides, etc. So we have done that with the help of our colleagues in the University of Twente with Professor Kees Wenner, where we can actually model in a simple PC computer of to 500,000 nodes or even more, depending on the modeling, if it is transient or steady state. And what we try to do here is to take a typical bearing topography And then we introduce some inclusions made of a stiffer material than the matrix. And then let us investigate what happens with those. So you can see that this is a lubricated problem. So you can see the hydrodynamic pressures here. You can also see the inclusions and how they concentrate the stress because they are stiffer than the matrix. But for this particular case, you see the clearances and the pressures. For this particular case, we did not generate a failure. Now, the same condition, but now we introduce equal stiffness, so you will not see this stress concentration because the stiffness is the same. You can see here. But now we introduce lower fatigue properties in the area where we have the inclusions. And then you generate the failure immediately here. You can see the failure. And this is typically what you will need to do if you want to model, for instance, the remelting of material coming from an electrical discharge in the contact. Once you generate a crater from electrical discharge, you basically remelt the material and you soften it. And it will have the same stiffness, but it will have very low, much lower fatigue properties than the rest. So it's interesting just for the record. There is another important failure mode that we see appearing in these electrical mobility conditions, which is what we call seizure failure mode, or other people call it, skidding or adhesive wear or smearing, etc. There are many names, but here we refer to the adhesive wear really produced by contacts running at very high speed and very high load. And if you remember the lectures in elastohydrodynamic lubrications, we see that in the past, there was many people still doing now, many people running experiments, increasing the sliding speed in the contact and increasing the pressure until the contact failed. And it fails by a very quick increase in friction and then the catastrophic failure eventually. And this failure is a thermal failure, is produced by high temperatures. There is a sort of line here that you cannot cross because the contact will fail. And it depends obviously on the temperature you are doing the experiment as well, and the lubricant and the additive and many, many other aspects, the roughness as well. But in reality, for every contact, there is one line here, and that is called the transition diagram. Now, it is very important to develop these transition diagrams for specific machine elements like rolling bearings or gears. In a rolling bearing, you will see the failure starting to appear like this one, with tiny micro cracks here. But if you look into the raceway, you will see that there is discoloration due to the high temperatures. And this is an indication that this is not regular surface distress, but it's actually the beginning of what we call seizure failure mode. The way to model this is relatively simple as well. You isolate the contact with the highest load. You need to model the starvation because we are running at very high speeds here. So starvation is very important. From that, we calculate the percentage of metal to metal contact that we may have in a mixed lubrication model, an average friction coefficient, and then we can calculate, or you can use the local friction coefficient if you have a numerical scheme. And then we can calculate the local temperatures on the surface. And if you draw these temperatures versus speed and pressure, we get these isothermals, which is basically the transition diagram. The only thing you need to do is to place an experiment to know which of these isothermals is the one that you are looking for as the transition diagram of your problem. And in this case, this is actually an experiment. It comes out to be around 250 degrees, more or less. But that can change with the lubricant that you are using. This is very important tool for you not to go beyond the limit of the machine or the machine element that you are modeling. With this, we are getting closer to actually trying to calculate the life of the contacts. Now, If you remember, the life of one single machine element like a bearing or a gear is almost impossible to calculate individually. You need to calculate the life of a population because seemingly equal bearings have small differences, even if they are working under very similar operating conditions. There are always small differences that will make the individual life of the elements very different from one to another. So what we normally do in bearings and also more and more in gears is to calculate the life of populations. So in this case, we calculate with 90% reliability. This is why we calculate the L10. It means that 90% of the machine elements will survive this life. And the way we used to do that in the past was basically by using subsurface fatigue, Hertzian stresses. And that will give us this damage integral that eventually will give us the life. But more and more, we realize that the surface is important. Before, we used to penalize the subsurface fatigue with a factor here due to poor lubrication or contamination or something else coming from the surface. But nowadays, we try to introduce the surface in the formulation. So basically, you have two damage integrals, one linked to the subsurface and one linked to the surface. In this way, we have much more flexibility. For instance, this integral can very well be calculated with a sophisticated numerical model as the one you have seen before for surface stress. Now, applications of this concept. We have used this concept, for instance, to assess the effect of individual indentations that we can measure in a raceway. We have also used this concept to assess the life of hybrid bearings, which have a very interesting tribology, very different from steel. So it's also considered in this model. And also the extension of this concept for gears, that is also a reality. So I invite you to read these papers, and I hope with this you will understand this concept a little bit better. With this, I just would like to finish with my conclusions. So basically, you can see that when it comes to electrification due to mobility, most of the tools that we need to model those phenomena in the contact are already there. We need to use it. Another important conclusion is that the tendency nowadays doesn't seem to be just to understand a single tribological situation or phenomenon, but actually the interaction of those and the competition of those phenomena are important for us to understand how to model failure modes, because there is always competition of different things. Now, the other important conclusion I could say is the tendency nowadays is to consider more realistic aspects of the materials. Materials are heterogeneous, polycrystalline, but also the lubricants. Their actual rheology of the lubricants is important. And finally, there is a tendency to actually separate the surface aspects from the subsurface when it comes to the modeling of rolling contact fatigue. And with this, I would like to finish my presentation. I'm ready for questions.
Thank you very much, Guillermo. So there's a couple of questions from our listeners. Yes. Ryan Notai asks, do you think there are any tribological concerns with increased battery power? For example, concerns with electrical damage at higher outputs?
Well, electrical damage has always been a concern, and I think if we increase the power, it becomes even more. Yes, now the solution that we recommend that is obviously the one that has no defect, I would say, is to use hybrid contacts, hybrid bearings, for instance. Electrical current cannot go through them. They have a fantastic tribological performance. They are, yes, a little bit more expensive, but it all depends on the particular solution that you are pursuing.
Thank you very much. And maybe that's all the questions we have time for today, but all the questions I want to remind will be answered afterwards under the video. And over to James now.
Yeah, just like to close the meeting now. Thanks for everyone for attending. Thanks to Lars and to Guillermo for their great talks. As I say, if you've got any more questions, please feel free to add them to the video and they'll be answered afterwards. Thanks to our sponsors. And just to say that next week's meeting is at the same time with Clelia Righi from University of Bologna and Reza Espinosa-Marzal from the University of Illinois. We've also got on Thursday the Twitter conference, so encourage you all to get involved in that. And yeah, for any more details, just look at our website. Thanks everyone, and see you again next week, if not at the Twitter conference. Thank you very much.